So welcome to lesson 1.3. This review, these questions, these come from mostly lesson 1.2. Domain and range we got into on lesson 1.1, but this is over lesson 1.1 and 1.2 here, domain and range. Remember, domain is dealing with your x-axis, range is dealing with your y-axis. Questions number 2 and 3 are specifically from the lesson 1.2. So if you want to complete this, go to lesson 1.2 and watch over those videos if you're struggling figuring out how to complete all of these. But I'm going to help you out, not by doing this problem here. I'm going to leave this for you. And don't note that here's your attendance link if you haven't filled out your attendance already. What I'm going to do is I've gotten some problems that are a lot harder difficulty, and I want to work those out for you. And so then you can come back and work on this if you've been struggling. If you're ahead here, then this ought to just help you out without you needing it for these problems. Okay, so for this first one, I've added this problem here, this difficulty, and I want you to take a look at our problem. Let's note some obvious differences. The bell ringer, its graph had one piece of graph. It was just this one piece. Notice on this one, how many pieces of graph do you see?
3.
3, very good. So when we work this problem, the domain could be as many as 3 pieces, and so could the range, but it doesn't have to be 3 separate pieces, as we'll see as we go. So the technique I've been teaching you is what's called trash compactor. And if you wouldn't mind, into the chat now, not audibly, but through the chat, type, if you know what a trash compactor is, please type in yes. If you don't, please type in no for me, just so I know kind of where we're starting from. If you know what a trash compactor is, type in yes, and if you don't, type in no, please. So no is the overall answer here. We don't know what a trash compactor is. So here's the way a trash compactor works. What happens is someone throws garbage into a trash can. And then you have somebody who comes by each week that picks up the trash, and those big dumpsters, those big trash dumpster vehicles, if you know what I'm talking about. What happens is they throw all the trash in, and to make room when they get to the next house, what they start doing is compacting all the trash. So basically the walls close in on all the trash like this. And when the walls close in, all the trash gets smashed in. So I want you to think of this in those type of terms. These 3 pieces are going to be smashed into the y-axis. That's how I want you to think of this problem here. So with that in mind, we're going to try to determine the domain and range. So I'm going to first look in this piece over here on the left, and I'm going to refer to this piece being the red piece. And so when we smash everything to the x-axis, everything gets smashed straight down. So this arrow is pointing, I'll say it's about on this line here. So I'm going to draw it straight down and put the arrow this way. It's now being flattened out. So this whole graph gets flattened down to the x-axis. And so this top part corresponds right here. And this part would get shifted up. It would get compacted up to the x-axis. So we're going to do an open circle there. And since the graph was connected the whole way, I'm going to connect these 2 symbols. So what I've done is I've taken this curve that's starting to look like a parabola, and I have smashed it with these trash compactors to where, whoops, I clicked the wrong button. I'm sorry, something pops up on your screen. Here we go. I'm trying to compact it by using this. All this gets smashed into the x-axis, and so I'm trying to flatten out the graph. That's really what I'm doing. And so in this part, smashed all this, and so this first piece, yes. And so to pick back up, everything gets smashed to the x-axis. And so I want you to envision this first curve here, this parabola being smashed and flattened. And so it now looks like this. Notice everything went to the x-axis. This arrow went straight down. This open circle went straight up, and I just connected at the center. The second piece, I'm going to do the same task. I'm going to call this piece the green piece. So imagine this piece getting flattened straight down. So this dot falls straight down. And since it's in green, I'm going to fill it in. It's a closed dot, and this is a closed dot, and it falls straight down to the x-axis. And since it's connected, I will connect these two green dots. And so there's my second piece here. And finally, we'll look at this last curve. We'll call this the blue piece. So the blue has an open circle and an arrow on this end, and it's connected the whole way. Okay, I'm going to pause and ask if you are understanding what I am saying. So what I've done is I took the arrow and dropped it to the x-axis. I took this open circle, moved it up to the x-axis. Those were in red, and I connected them with a solid line. I then went to this piece. I dropped its dot and its dot, the two places, and I connected them with a green line. That green line right here represents the second piece of graph. This third piece of graph right here, what I did is I moved this open circle up to the x-axis, I moved the arrow down to the x-axis, and I connected them. So I now have my three pieces of graph, and instead of it looking at as the whole graph, I'm now only looking at domain, the x values. So to proceed from here, what you need to do is look at, are there any breaks in this graph? And what a break would look like is something like this. This would be a break in the graph. There would be an open space. That's a break in the graph. When you look at what we have drawn, do we have any breaks in these three different colors? Are they broken apart or are they all connected?
Connected.
They're connected. So this domain has no breaks. And this arrow means it goes left forever to negative infinity. This arrow means it goes right forever to positive infinity. So we could describe the domain of this graph. The domain could be described as going from negative infinity to positive infinity. Or another way of saying this is x is all reals. So the answer to this one's domain is all reals because there is no break in this line. It's connected the whole way. And our three pieces here that I drew on the x-axis, it's connected the whole way. There's no gaps. There's no breaks. Even though this blue is an open circle, it's filled in by the green. This dot right here fills it in, and so there's actually no gap whatsoever on this, and so the domain is all reals. So I'm going to show you this picture one more time without my writing on there, and I want you to look at it. It looks like three different pieces of graph, and it is three different pieces of graph. One piece, two piece, three piece. It's three pieces of graph. But the domain itself is all reals because it goes left forever, it goes right forever, and these gaps in between these pieces, if you smash this to the x-axis, they fill one another in. So there's actually no break in the x-axis. This graph exists everywhere along the x-axis. For that reason, it is all reals for the domain. However, the domain, or excuse me, the range would be different. Let me show you the range. So this time I'm going to take my graph, and instead of smashing to the x-axis, I'm going to change this so it gets smashed to the y-axis. Sorry, my Zoom tools are taking over. Here we go. So I'm trying to change my trash compactor. Instead of flattening it to the x-axis this time, we're going to flatten to the y-axis. So imagine this graph getting smashed to the y-axis. I'm now finding range. So this comes in, this, whoops, that's not what I wanted to do. And then this piece comes in, and they flatten everything to the y-axis. So that's what I'm doing this time. And so I'm going to take my red piece. This arrow is way up here. This open circle is right here. What's weird to connect this is it doesn't just connect from top to bottom. This time, notice how it went lower first. That means this graph, if it got smashed in, would go lower first and then back up all the way until we reached the very top of the arrow. So it's going to go all the way up here like this. This first piece got smashed in, and so it has an arrow up top. It had this open circle, but the graph itself goes down, and then it fills itself in. Why does it get filled in? Because this dot right here is not an open circle, it's a closed dot. So it fills itself in when those get smashed together. And so I have this as my first part of range. Now I look at this second part in green. If this got smashed to the y-axis, what it would become is just one solid dot right there. Because both of these two pieces, everything will get squashed right there. And it's just one solid dot. Now this piece, when it gets squashed over, this comes over here like that. Open circle. This arrow is about right here. And then you connect these. Now I want you to look. This red line is filling in this dot. Wherever the open circle is, this red line fills it in. So again, as I look at this graph, there is no break from the top to the bottom. There is no open circle that remains open. There's no gap. This whole thing is filled in. So it goes up to positive infinity, but the graph this time does not go down forever. This graph actually stops right there on that top point. It doesn't go forever down. It stops right there. So how low is that point? Let's see. Oh man, my axis is off. That's -2. I guess that makes that -4. This is, I don't know how this is counting, but it looks like this is I'm going to scratch out this number to make it easier. We're going to say that's -1, -2, -3, -4, -5. This line's -6, -7, -8, -9, and we're going to call this -10. This time the graph goes down to -10 and goes up to infinity. So the range would look like this. It would be from -10, I'm going to use a bracket, because it's not an open circle. Unless it shows me an open circle or gives me an arrow, it's going to be a bracket. If it gives me an arrow for infinity, it's a parentheses, or if it gives me an open circle at the bottom, it would be a parenthesis. Other than that, it's going to be a bracket. So from -10 to infinity is the range. Or you could say that -10 is less than or equal to y. And when you write in this form, you don't have to write less than infinity. You don't have to include infinity, so I can leave that away. These would be the two ways of writing the answers. So I'm going to pause the recording and let y'all talk about what is different on the range as opposed to the domain. Okay, so a great question that comes up is, do I have to write the values in this order? And the answer is yes. You always write to the smallest number to the largest number, that order. So in this case, I put the -10 before the infinity because -10 is smaller, the infinity is larger. Said another way, if you're looking at domain, you always go left to right. That's the smaller, that's the larger. If you're doing range, you go bottom to top. These are the smaller, this is the larger. So it's always smaller to larger, smaller to larger. You always go in that order. Now, I'm going to show you something that will, unless I point it out, will later in the year confuse you. So I want to point it out just so you can see, okay, so there can be a difference here. When I look at the actual graph itself, so I'm erasing all my junk. When you look at the graph itself, I want you to notice something. This graph had 3 separate pieces on it. There were 3 pieces of graph. 1, this curve, 2, this flat line, and 3, this curve. There's 3 pieces of graph. If you have 3 pieces of graph, does that mean your answer for domain and range will have to be 3 separate pieces? Answer, no. The domain here only has 1 piece. And these are 2 different ways of writing it, but this is 1 piece. This is 1 piece. This means the answer was 1 interval, even though the graph had 3 pieces. So you can have 1 piece of domain even if you have 3 separate pieces of graph, and the same for range. We had 1 value for the range even though there are 3 different pieces. So they don't actually correspond to how the graph looks. When you look at this graph, you say, oh, there's 3 breaks. I better have 3 separate parentheses, 3 separate values with U's. A lot of students think this, oh, and maybe some will be a bracket, sure. Maybe I'll have a bracket there and a bracket here, but I'll have these U's to give me 3 separate pieces. That's not always the case, especially the more you advance in mathematics. You see strange graphs that even though they look like multiple pieces, when you find domain and range, the pieces connect together. Now, that's not always the case. So I got a second example. We'll call this one example 1 here. And so there's the domain and range for example 1. Now let's look at example 2. And so again, I have the same basic setup. Notice I have 3 pieces of graph. I have 3 pieces of graph. Does that mean my domain will have 3 pieces necessarily? Okay, so let's find domain and range. I want you again to visualize a trash compactor here. So a trash compactor, if you just think about the garbage truck that comes by and picks up your trash, it throws it in and then it collapses the walls to smash it all up to make more room. So imagine this is the trash bin. Here's some garbage in it, and the bin walls start to close in for domain on the x-axis. They take everything, whoops, to the x-axis to make some space. So all that gets smashed in. And so we take this trash and we're going to smash it in. We'll call this our red piece. The arrow's here, it goes straight to the x-axis, so it's now there. There's its closed dot. I go straight down to the x-axis, and now I connect the 2 symbols. Are you following me so far? Yes or no?
Yeah.
Yes.
Okay. I move on to the second piece. We'll call this our green piece. So I take the open circle right there. I take this open circle. And again, I'm taking everything to the x-axis because I'm doing domain right now. And now I connect the 2 pieces. And now I go to my third piece. We'll call this the blue piece. Its symbols fall straight to the x-axis. And now I connect them with a line. And so the question is, for this problem, when you look at the x-axis, do you see any breaks? Do my colored lines break apart anywhere? Or are they all connected like the last problem?
They break apart.
They broke apart.
There's a break. This problem has a break here. And we also need to check this. One symbol's open and the other one's closed. Does the closed fill it in? Answer, yes. So you don't consider that is not a break there. Not a break. The reason it's not a break is because this closed dot fills in the open dot. They fill it in. So that's not a break. So this domain is going to have 1 break. So let's do our domain. How far left does this arrow travel?
Infinity.
Negative infinity. So it's going to go from negative, which always gets a parenthesis. Arrows get parentheses because they don't actually get to that spot. They just are heading that way. All the way up, and the first break is right there. And counting the x-axis, 1, 2, 3, 4, 5. It's going to break at 5. Does 5, open circle 5 here, get a parenthesis or a bracket?
A bracket.
Correct.
Very good, bracket.
Okay.
Open circles are brackets. Excuse me, I am totally wrong there. What am I saying? Open circles get parentheses. I'm sorry. Open circles get parentheses. Brackets go with closed dots. So this goes from negative infinity to 5. Now we have a break. The way you symbolize a break is you put a U, and then we continue on. If this x value is 10, that means this x value is 9. It goes from 9 to infinity. Open circle, so that means parenthesis. 9 to infinity. There's our domain. If you were going to write this using inequalities, you would say x is less than 5. You don't have to include the infinity parts. Say x is less than 5, because the x is like in the place of comma. Since it's a parenthesis, it's just less than, not equal to. Less than 5, or, that's what the u is, or x is greater than 9. So x, this one is a smaller number, x is in the middle. X is bigger than 9, or it's less than 5, one or the other. That's the other way of writing this answer. Now let's look at the range. So with range, I need to erase all this, and I want you to envision all this graph being taken to the y-axis now. Okay, so that goes away, and now we're going to take this to the y-axis. I'm not, for the sake of time, going to draw my trash compactor lines. I want you just to visualize. So imagine this part of the graph being smashed to the y-axis, this part being smashed to the y-axis. So this arrow gets smashed across to here. I'm doing it in the wrong color. I need to do this in red. This arrow gets smashed across to the y-axis like this. This closed dot gets smashed there, and I connect this first piece. So this first piece here gets smashed there for range. Now I take the second piece, open circle, connect with the line. Finally, the blue piece. Open circle, straight across, arrow, this. Okay, as we look at this, I have an open circle and a closed circle. What does that mean if you have open and closed? Does that mean it's open, or does that actually mean it's closed if you have both?
Closed.
Closed. That's right. This red graph closes the point. This one's closed. So I fill it in. So there's not a break. No break. The red fills in the spots. So there's no break there. Okay, what about here? I have a green with the open circle, but the red with the solid line. Does that fill it in or not fill it in?
No. Yes.
Well, it's like a dot here. So yes, it fills it in again. So there's no break there, nor is there a break there. We got no breaks so far. So I keep going down. Now this looks like the stop of the graph, but what does this arrow mean right here? What does that
Infinity.
arrow mean? It means it keeps on going to infinity. So I could keep drawing that down if I wanted to. Just like up here with this arrow, I could keep drawing it up if I wanted to. So this graph for the range is actually going to go from negative infinity to positive infinity. There are no breaks whatsoever. So we would either write negative infinity, comma, positive infinity, or you would write Y-E-double-R for Y is all reals. So that's how you do domain, and I just gave you right there very difficult problems. Those were not easy. Your problem for the bell ringer was just this graph. Now, if you take the same process, you'll probably be able to solve that real quick. I'm not going to go over y-intercepts and zeros other than to say a zero is another name for a x-intercept. So where does it cross the y-axis? Where does it cross the x-axis? That's basically what you're doing in number 2. What I am going to talk about is symmetry. So let's go to, with symmetry, you can have 3 types of symmetry. And let me just add a page here. Insert blank page. Okay. You can have 3 types of symmetry. You can have a graph that's symmetric with the y-axis. So this is symmetric across y-axis because it reflects on the y-axis here. You could have, technically you could have 4. Let me add 4. The 4th one's going to be hard for me to draw though. You can be symmetric across the x-axis. And I'll get a different shape here. Like that. That's a graph that's symmetric across the x-axis. The x-axis cuts it in half. Here, the y-axis cut it in half. You can be symmetric across the origin. So something that's symmetric across the origin. It'd be like if you had a star over here and a star over here. Those are symmetric across the origin. And then finally, you could have symmetric over the line y equals x. And so let me see if I have a dotted line to help me out here. Yeah, your graph would look like this. If it was something, I'll just use one of their shapes again, smartboard shapes. And I'm going to rotate it. Oh, wake up, computer. Something like that. That's on the line y equals x, it's split in half. That would be symmetry across y equals x. There we go. So those are the 4 types of symmetries. So you can have across the y equals x, across the origin, which that looks like y equals x. Let me, well, across the origin, y equals x is more referring to it reflects this way. I could change the shape. This will make it easier. No. Sorry, I clicked the wrong thing. I want to click this. And to make this easier, now it's not reflecting across the origin. So across the origin literally means it goes across this. That's the reflecting point. Y equals x, it doesn't have to go across the origin. It just reflects through the middle of the first quadrant or the third quadrant. That's what it means. Okay, so those are 4 different types. Now there's some extra names that come with it. If something reflects across the y-axis, it's an even function. So make a note on this. This would be an even function. And then I will get to your work. That's an even function. The other one you need to know about is if it's symmetric across the origin, this means it's an odd function. The other 2 are not neither, nor they're not even, nor are they odd. So that's an odd function. This is an even function. So from lesson 1-2, I went over some symbols, and I want to go over it now, just to help you out on understanding this stuff. So here, I give you these symbols, and for a lot of people, this might as well be a foreign language when you see this, but this is just math ways of writing something. Here's what I want you to realize. The f itself refers to the y value. The x value refers to the x. So going off, knowing a point is x comma y, here's what I'm going to ask. This value right here, what is negative? Is it the x that's negative or the y that's negative? When you see this, the x is negative. So I have a negative x value, but my y value itself is positive because the f is positive. The f is like your y. So I have a negative and a positive for the y. That's a negative x, and a positive y. Okay, now let's look at the second point. Over here, this time my x is positive and my y is negative. So if I wanted to see what type of symmetry do I have, here's how you solve this. You first write out if it's a negative x, negative y, positive y, just like we did. And then you just, what I do is I just draw stars to represent the points. This point, since it's a negative x, means it's left. This is left, this is up. Negative x means left, positive y means up. I'm going to put a green star in the second quadrant because this is left and up. Over here, I have a positive x and a negative y. This means right and down. So I've taken this foreign language of symbols, foreign language of math symbols, and I've represented it with 2 stars. And now I'll ask the question, does this reflect across the y-axis? Does it reflect across the x-axis? Does it reflect across this diagonal line, or does it reflect across the origin? Where does this reflect? Across the y, across the x, or across the origin? Just keep it simple.
Across the origin?
Across the origin. So this is symmetric across the origin. Come on. Symmetric across the origin, which means it's an odd function because the O's go together. If it's symmetric across the origin, it means it's an odd function. And this would be the answer here. I know if you're reading the instructions, I didn't say where does it have symmetry, I'm just adding it in. Since it's a symmetric across the origin, that means it's a odd function. I'll go back to the previous slide. If we have symmetry across the y-axis, it's even. If it's across the origin, it's odd. So O's go together. And if I stop sharing my screen and you were able to see my face, I would say this: even is kind of like your face. Your face is even and it divides across the y-axis. Here's the y-axis. My face is evenly distributed that way. It's an even function if it divides evenly like that. Your face is not odd. Your face is even, and it's this way. Odd goes across the origin. Odd goes across the origin. So the first problem I just showed you goes across the origin. That means it's a odd function. All right, let me try you 2 more examples. This time, I throw in new symbols. So the process is still the same. Whenever you're determining if something's even, odd, or neither, you look at each value. And so this time, my x, is my x here positive or negative? Is this x a
Positive.
It's positive.
Positive.
That means it's going to be on the right side of the graph. My y value, is my y value positive or negative here?
Positive.
Positive. That means it's going to be in the first quadrant. It's going to be right and up. Now my second point. That absolute value is technically only on the y. So we say we have a positive x and the absolute value of the y, which it looks positive as it is. So it's absolute value of a positive. Now, if you remember, absolute value just means turn everything positive. So this positive stays positive, and that just makes this become positive, positive. Whoops. Positive, positive. Because absolute value of positive is still positive. So if I graph these two to check for symmetry, this says go right and up, put a star, right and up, put a star. This also says go right and up, put a star. Notice they're on top of each other, so there's no symmetry. Because it's not being reflected, they're just right on top of each other. No symmetry, so since there's no symmetry, it's neither even nor odd. And this would be your answer. There's no symmetry because it does not reflect. It's just on top of each other. There's no reflection. So if there's no reflection, there's no, it's not even or odd. It's not symmetrical. And I got one more. This time I'm going to show you. So this is kind of like how when we're tested, oftentimes we test in this form because it challenges whether or not you understand math language. But on your homework on Alex, they a lot of times will test you on a graph like this. And so here's what you do if you aren't given the math language but actually given a graph, is you just pick 2 points. And so I can tell really quickly this is not symmetrical on the y-axis because this point does not reflect to about right there. So it doesn't reflect across the y-axis, nor does it reflect across the x-axis. Otherwise, then you have a point down there. So it does not reflect across the x or the y, across the y or the x. It doesn't reflect those 2 ways. But to determine if it reflects across the origin, what you do is you take 2 points and you write out what that point is. This has a height of 3 and its x value is almost 2. It looks like it's somewhere in there. I'm just going to guess, and I'll just say it's about 1.75. So I'm going to say the x value is 1.75. The y value is 3. How you determine if it reflects across the origin or not is these 2 values, you should just switch signs and you should get this point. So I'm looking at the x, and it looks like to me the x is about negative 1.75. And the y is negative 3. Do you see how these symbols just switched? I mean, the numbers stayed the same, but the signs just changed. If they both do that, that means it's reflecting perfectly across the origin. So this one is symmetric with origin, and I'll show you another point. Symmetric across origin. And if it's symmetric across the origin, that means it is a odd function. That's what it means if it's symmetric across the origin. It's odd. Now, let me show you another point. If we took this point here, it looks like it's about negative maybe 4.75. Let's call it negative 4.75. And it has a height of 3. And if I go over here to this point, this is positive 4.75, but the y value is negative 3. Do you see how the number values stayed the same? But what happened is the symbols changed. This was a negative, it became a positive. This was a positive, it became negative. If that's the case, it's reflecting across the origin. If all of it changes are the negatives like that, then it's an odd. So that's kind of a review of 1, 2, all the hard things. Today you're getting into 1, 3, which I already have the videos online for. If you go from Power School Learning, you'll go to chapter 1, and then 1, 3. Make sure you do your 4 things. Number 1, you need to take attendance. Number 2, you'll watch your videos and take notes. Number 3, you'll take your lesson exam bell ringers. And number 4, you'll do your ALEKS. Those are the 4 things that are required.